Now, the refrigerant leaves the evaporator at 20 degrees Celsius and has a pressure of 0.9 megapascal. Now, in this type of questions, there are two things that you will be given. It's either you'll be given evaporating temperature or evaporating pressure. So in our case, we are given evaporating temperature. Question 1, for both evaporating and condensing, we're given pressures. If you look at question 1 above, you'll see that the evaporating pressure was 0.14 megapascal and the condensing pressure was 0.8. In this case here for question 2, evaporation temperature is given, not the pressure. So I'll show you how to deal with the problem if you have temperature instead of a pressure. In fact, it's the same. If you have a pressure, you use the pressure table. Now it's a temperature, you use a temperature table. So there's no big deal about this question. And then we have a condensing pressure of 0.9 megapascal. The flow rate of refrigerant is 3 kg per minute. Now we are to find the coefficient of performance for a refrigerant as well as the coefficient of performance for reverse Carnot. And I'll briefly go through the Carnot. I'm not sure if you understand, but this is something that you should have done last semester when you were doing second law of thermodynamics. For the same Tmax and then Tmin and the times of refrigeration. So what we are told here, we are told now to calculate what? To calculate QL. This kind of QL, but in this case, the answer is not going to be in kilowatts. We have to express our answer in tons instead of kilowatt. Now you'll see that in modern refrigeration, in refrigeration, you'll find that sometimes, most of the times, the QL or QH is expressed in terms of tons or in BTU. BTU stands for what? British thermal unit. So 1 kilowatt is equivalent to, I think it's 3,412 BTU. So if you go to, if you have aircon at home, go and check the aircon outside the specs. You'll find that most of this time the specs are in BTUs or are in tons of refrigeration or in kilowatts. But in kilowatts, normally they don't really use kilowatts for refrigeration. They use tons of refrigeration or BTU. So 1 kilowatt is equivalent to 3,400 British thermal units. So in this case, we are going to calculate QL, but now it's not in kilowatts, but in terms of refrigeration. Okay, so how do we approach? We have to draw a TS diagram. Now in the exam, I will expect for all the questions, we have to draw a sketch. The sketch is going to show me whether you understand the question or not. If you don't have a sketch, and then your answer is wrong, I won't know whether you understand or not. So if you have a sketch, you might score a mark or 2 for the correct sketch. So in this case here, I'm going to draw a TS diagram of an ideal vapor compression system. So it's temperature at entropy. And then this is your compressor. It's point number 1 here. So between 1 and 2 is a compressor. The arrow shows the direction of flow. And from 2 to your saturation vapor line is the superheating. And then from 2 to 3 is a condenser. And then from 3 to 4 is an expansion valve. So this is a TS diagram of a vapor compression system. So I expect you to draw this in the exam, so that to show me that you understand what you are doing. Okay, so we said that 1, the refrigerant is dry-saturated, is HG, that is the enthalpy there. 2 is superheated. 3 is a liquid saturation. And at 4 is wet vapor. So QL is between 4 and 1, and QH is between 2 and 3, and compressor is between 1 and 2. So this is your TS diagram for an ideal system. Now let's see, we are told that the condensing pressure is, the evaporating temperature is -20. So where is -20? -20 is here because evaporation takes place between 4 and 1. So here we have -20 degrees Celsius. And then the pressure, because it's ideal, the pressure at 3, the pressure at that point, and the pressure at 2 is 0.9. P here is 0.9 megapascals, MPa. What else do we have? That's all we have. And then we know that the mass flow rate, M, is 3 kg per minute. So before we answer the questions, first of all, you have to determine all the enthalpies. Enthalpy at 1, enthalpy at 2, enthalpy at 3. Once you get enthalpy at 3, we know that enthalpy at 3, H3 is equal to H4. So there's no big deal about H4 because it's the same as H3. We are going to start with H1. H1, where we are right now, the refrigerant is dry, so it's Hg. H1 is equal to Hg at -20 degrees Celsius from the tables, which is equal to, and then we shift to the tables. And then this is a refrigerant 134A pressure table. No, we have temperature going to temperature table. Temperature table at -20. Here is -20. -20. So where is Hg? Hg and -20 is 238.43. 238.43. 238.43 kilojoules per kilogram. So this is at point number 1. Now, we know that the relationship between point 1 and point 2 is that entropy at that point is equal to entropy at that point. So S1, which is entropy at 1, is also Sg at 20 degrees Celsius from the tables. We go back to the tables to obtain S1. Where is 20? Here is 20. Sg is 94575. 0.94575 kilojoules per kilogram. Right, the question is, why do we need Sg? We need Sg because at 2, for us to get enthalpy at 2, we need 2 properties. Now at this point we have 0.9. For us to get enthalpy, we need another property, which is entropy. So we know that S2 is equal to S1 is equal to this value here, 0.94575 kilojoules per kilogram. So now we need enthalpy at 2. Enthalpy at 2, the steam is superheated here. The steam is superheated. So we go to the superheated refrigerant tables at 0.9 MPa, and so we say that H2 at 0.9 MPa and 0.94575 from tables. From tables is equal to, now we're going back. Let's go to the tables. at 0,9, superheated steam tables. Zero 0,18, 0,24, where is 0,9? 0,7, here is 0,9. Here is 0,9. Now, enthalpy is going to be here. So we are looking at 0,9554. So it's going to be between 0,9328 and 0,9661. That is our entropy. Our entropy is 0,94. So it's going to lie between 9328 and 9661, which means that our enthalpy is going to be between 274.19 and 284.79. So in the interest of time, I'm not going to interpolate. I've already interpolated here on my paper. I'm just going to give you the final answer. And after interpolation, at 0,9456, our enthalpy H2 is 278.29, which falls between, say, 274 and 284. I'm trying to say 10. So after interpolation, I found that my enthalpy at 2 is 278.29 kilojoules. So the homework is that, please, guys, when you have time, go and interpolate this value and that value to get the enthalpy. Okay. So the last one, enthalpy at 3 is equal to enthalpy at 4 is equal to HF at 900 kPa. 900 kPa, yes. 900 kPa is 0,9 megapascals. So because at 3, the refrigerant is liquid, is liquid saturated, we go to pressure tables at 900. We scroll up, and then we are looking for 900. 900 HF is 101.62. 101.62. So is equal to 101.62 kilojoules per kilogram. So guys, whenever you are trying to solve this problem, before you go to the tables, you must ask yourself, what is the condition of refrigerant at 3? Now, if at 3 is liquid, saturated liquid, it means that saturated liquid is HF at that pressure. So we are here. Now you go to 2. What is the condition of a refrigerant at 2? Superheated. Superheated at 0,9 and 0,9475. And then you go to 1. At 1, what is the condition or the state of refrigerant? Here it is HG. Otherwise, it's trisaturated, which is HG at minus 20 degrees Celsius. So once you get all the enthalpies, because for the sketch in the test is 2 marks. Each enthalpy is a mark. So it's 2, 3, 4, and then 5. You already have 5 marks even before you start solving the problems. We already have 5 marks. So the first question was calculate what? The COP of a refrigerator. So COP R, we said, is what? H1 minus H4, which is this divided by that, which is H2 minus H1. In other words, you can still say that is QL over compressor work. And then we substitute, we say that COPR is equal to 238.41 minus 101.62 divided by 278.29 minus 238.41, and the answer is 3.43. So this is 2 marks in the exam. 2 marks. So it's 5 plus 2, you already have 7 marks. Now, the next question says calculate what? Let's see. Calculate the tons of refrigeration. I'll come back to a COP R later. Tons of refrigeration, I said this tons of refrigeration, this guy here is the same as QL. But in this case, this guy is in tons, not in kilowatts. So tons of refrigeration is coming from H1 minus H4, but the units are in tons, not in kilowatts. So we say that QL is going to be the mass flow rate, bracket, enthalpy at 1 minus enthalpy by 4. Then we say multiply by 1 divided by 211. What does that mean? It means that 1 ton of refrigeration is equivalent to 211 kilojoules per minute. So this 211 is kilojoules per minute. Now, when you're calculating tons per minute, tons, this M is not going to be in kg per second, is in kg per minute. So M is 3 kg per minute multiplied by enthalpy at 1. Enthalpy at 1 we said is 238. 238.41 minus 101.62. The units are kilojoules per kilogram multiplied by 1 ton divided by 211 kilojoules per minute. So this minute will cancel that minute. This kilojoule will cancel that kilojoule. This kilogram will cancel that kilogram. So we are left with only 1 ton. And the answer is 1.945 tons of refrigerations. This is our answer. But if you are to express it in a kilowatt, you remove 1 over 11 and then you convert that kilojoule kg per minute to per second. But in this case, the question says determine QL in tons of refrigeration. That's what the question looks. The question is asking for. The last one, the question says calculate COP of Carnot cycle. Let me first just solve it and I'll explain it afterwards. So COP, Carnot, R Carnot, it is 1 divided by TH divided by TL. TH is Tmax and TL is Tlow minus 1. Now TH, in this case here, what is TL? It is going to be minus 20. So minus 20 plus 273. And then TH, let me just write it down. TH at 900 kPa from the tables. Now you go to the tables and then you go to 900. 900 is 35.51. 35.51 plus 273. And then TL. How do we get this TH and TL? All you need to do, TL is here, lowest temperature is here, and the highest temperature is there. So TH here is 35.35 degrees Celsius. So your Carnot is operating between these two temperatures, between the extreme temperatures, the highest temperature and the lowest temperature. So 35 is coming from the steam tables at 900 kPa because the pressure from 3 up to 2 is 900 kPa. Now, I'm going to challenge you to say, okay, TL is going to be negative 20 plus 273, and then we can calculate our reverse Carnot, which is 1 divided by 308.51 divided by 253 minus 1, and the answer is 4.566. So this is the maximum any machine can actually get, but this is not a practical cycle or efficiency, because it does not take into account any wastefulness or irreversibilities in the system. It only focuses on the temperature extremes, the high temperature and low extremes. So any other machine that is cannot give you. This is the maximum efficiency any machine can give you. Now I want us to go back to Carnot.